All right. So now what we're going to do is, since we've talked about this valence shell electron pair repulsion theory, looking at only bonding groups representing our electron groups, we're going to look at exchanging those bonds for lone pairs. And so at this point, we have to define a important distinction between two different ways we're going to talk about shapes of molecules. And so we'll call the electron geometry the geometry of your electron groups. So this is going to be independent of if you have bonding bonding groups or not, or lone pair groups. So independent of type of electron group. And then we're going to have something called the molecular geometry, which is just going to be the geometry and arrangement of atoms. And so this is going to be dependent on presence of lone pairs, because those lone pairs are not going to show up in what we observe in the arrangement of atoms. And so what we'll see is that when the electron groups around the central atom are not just bonds, we get some new shapes. And so these lone pairs, which instead of being shared between two elements are just existing on a single atom, they occupy more angular space. So they just take up more general space than a bonding pair of electrons. And you can think of this using this image below, where when you have a shared set of electrons, they take up a little bit, a fair amount of space. But when you have a lone pair, it gets a little bit wider because it doesn't have to narrow in on being attracted by another group. It gets to explore a much larger space. And so because it occupies a much larger space, it tends to push those bonding groups away. And so if we look at something like NH3, and we look at its electron geometry, so how each of the electron groups are oriented relative to each other, we have 3 bonding groups and 1 lone pair. And so that's a total of 4 electron groups. And so when we look at the electronic geometry, we have the electron geometry corresponding to 4 electron groups, so tetrahedral. But when we look at the molecular geometry, when we don't get to see that lone pair, we see that we get something called a trigonal pyramidal geometry. And in that trigonal pyramidal geometry, we deviate and change from that 109.5 degree separation because that lone pair takes up more space. So in our trigonal pyramidal geometry, we see that instead of 109.5, we get a separation closer to 107. And so that's when we exchange in our tetrahedral electron geometry, we lose one group to lone pairs. And so there's one more form of a different geometry when we look at the tetrahedral electron geometry. And so already we've talked about molecules with one lone pair that have 4 electron groups adopt the trigonal pyramidal geometry that we saw with NH3. When you change out one more of your bonding groups for a lone pair and have 2 lone pairs, what you'll see is that these molecules adopt a bent geometry. And a great example of this is water. And so with water, we can see we have 2 bonding groups and we have 2 sets of lone pairs. So that gives us 4 total electron groups. So that's how we got that tetrahedral electron geometry. And then when we take those 2 sets of lone pairs and let them take up space, what we're left with is these 2 hydrogens right here around the oxygen in a bent geometry. And like I said, we'll talk about this a little bit more in the molecular models lab, but effectively we just take away 2 of those groups and we end up with, this kind of V shape. And similar to our example with ammonia, when you have a electron geometry and a molecular geometry that match, you get that ideal separation of 109.5. When you get one lone pair, that narrows to 107 degrees. And when you switch out for 2 lone pairs, you see that minimizes to 104.5 because you just have more repulsion by those lone pairs. So now we're going to look at cases of where we take a molecule with trigonal bipyramidal electron geometry. So that means 5 electron groups. And we're going to sub out 1 electron group at a time for lone pairs. So when you have 1 lone pair, what we'll see is that this will adopt what we'll call a seesaw molecular geometry. And so what we'll do is we'll take away one of the groups that are in the triangle. And that's because if you take away, excuse me, if you take away one of your groups that are, in the axial position, what you have is a lone pair that is now 90 degrees away from 3 separate groups. And so it's very close to all of those elements that are in the triangle. And so we have 3 of these 90-degree lone pair bonding pair repulsions. If you take away instead one of your groups that are in the triangle, you have only 2 90-degree pair repulsions, and then you have, excuse me, you have these 2 120-degree repair, sorry, 2 120-degree pair repulsions. And so even though there's, one more type of repulsion, you only have 2 that are 90 degrees, so 2 that are close, and then 2 that are far away. And so we favor having the fewest of these close electron pair repulsion interactions. So we favor taking them away from the axial position, we take away from the equatorial, and we get a seesaw. So two of them are a little base of the seesaw, and then your axial positions are the 2 seats of the seesaw. If we take 2 of the electron groups and exchange them for lone pairs, what we see is that we adopt a T-shape electron geometry. And in this case, we once again remove, excuse me, we once again remove one of our axial positions because this helps us to minimize this 90-degree pair repulsion. We are, we end up with something that looks like this for our bromine trifluoride, where we have our 2 axial positions and then our equatorial position. And then if we finally have a substitution of 3 lone pairs, the shape that we end up with there is just going to be linear. So we take away one last equatorial position, and then we end up with a linear geometry. And all of this is that we want to take away we want to put the lone pair in a position that minimizes electron repulsion, or close angle electron pair repulsion. Then our last one is when we look at our molecules with octahedral electron geometry, so meaning that they have 6 electron groups. And so with this, what we'll see is that when we have 1 lone pair, we're going to adopt a square planar electron geometry. Sorry, not square planar, square pyramidal. So we're going to take away one of our axial positions. And then if we switch it out for 2 lone pairs, we're going to adopt a square planar. electron or molecular geometry. Square, planar, molecular geometry. So once again, just choosing these to have the best amount of separation between everything. Okay. Excuse me. And then, so this is just a table summarizing our different electron geometries and molecular geometries. So when you have a set number of electron groups that are bonding and having lone pairs. And so you can take your time to look at this. We've effectively talked about all the different options for this part of the table as well as this part of the table. So subbing out one bonding group at a time for a lone pair. And so what I want you to do right now is to look at the following electrons and determine the electron geometry as well as the molecular geometry. So I'll have you pause right here, and then we'll answer that in just a second. Okay, welcome back. And so if we look at NH3, this has 3 bonding and 1 lone pair. Water is 2 bonding and 2 lone pair. ICl4 minus, excuse me, is 4 bonding and 2 lone pair. And then PCl3 is 3 bonding and 1 lone pair. And so what that means is that we have, for the electronic geometry, which I'll just put EG for electronic and MG for molecular, electron geometry, we take the sum of our bonding and lone pairs. So that's 4 electron groups. So that's tetrahedral. Let me just write that a little bit better. For H2O, we have 4, so that's also tetrahedral. For ICl4 minus, that's 6, so that's octahedral. And then for PCl3, that's 4, so that's also tetrahedral. And then when we look at the molecular geometries, we're going to look at, our number of bonding and our number of lone pairs. For NH3, we take one group from a tetrahedral, exchange it for a lone pair. So that gives us our trigonal pyramidal. For H2O, we take out 2 of those groups, so this gives us bent. For ICl4 minus, we have 2 lone pairs, so that gives us square planar. Just basing this all off of that table above. Then finally, for PCl3, this is once again 3 bonding, 1 lone pair. So just like NH3, this is trigonal pyramidal. Okay. And so what we're going to talk about in the next video is about molecular polarities. So using these shapes and the polarity of each of the bonds to see if the total molecule is polar or nonpolar.